to this octet rule. Boron is one. Boron tends to form compounds in which the boron atom has fewer than 8 electrons around it, so it's not going to have a complete octet. It's called an incomplete octet. This is the Lewis structure for boron trifluoride. I got my boron in the middle. Boron kind of only wants to form 3 bonds. It's going to give up some electrons. It's going to give them over to the fluorine. That fluorine is going to have its octet completed, and the boron will be a incomplete octet. These borons only got 6 electrons around it. By adding a double bond, it's going to satisfy that octet rule, but you're really just going to not want to do that with your fluorine. And what's going to happen instead is that you're going to form like some of these stable dimerized compounds with boron. Things that are going to expand the octets or exceeding the octet rule. If you're beyond period 3, you've got the availability to mess around with some of those d orbitals. So the Lewis structure for sulfur hexafluoride. All right, you're going to start off with 6, and then 6 times 7 for 48 electrons, and you end up with a Lewis structure that looks like this, right? I've got some happy fluorines, and then my sulfur here has got a bunch more of extra electrons in bonds than you would expect, right? It's actually shoving some into some d orbitals, right? So our octet rule is also going to be violated for phosphorus pentachloride. So we're going to add up all our valence electrons, 5 for the phosphorus, 5 times 7, 40 for the total thing. And then we're going to end up with phosphorus in the middle, surrounded by these chlorines. I've got 1, 2, 3, 4, 5. I've got 2, 4, 6, 8, 10 electrons around phosphorus. So you are violating and expanding the octet of the phosphorus. So it's exceeded that electron rule by 2. So when it's necessary to exceed the octet rule for one of the several third row or higher elements, assume that the extra electrons are going to be placed on that central atom. So the central atom is going to hold more. And we will see when we do VSEPR that there's going to be some rhyme and reason to that, why it's going to do that. So calculating the valence electrons present in triiodide, for example, you've got I3 minus 3 times 7, and you got a negative charge, it brings you an extra one in, that's going to give you 22 valence electrons. You're going to end up with more electrons around that central iodine than you would have in the octet. Right. Looking at a couple more examples, we'll do chlorine trifluoride, xenon oxide, radon chloride, beryllium chloride, and iodine tetrachloride. So if we do the chlorine atom in our chlorine trifluoride, we're going to have to bond something to this chlorine. The chlorine is going to have to be this central atom. The fluorines will go on the outside. They'll complete their octets. Chlorine's going to expand it, right? It's going to accept some extra electrons. If you are a noble gas, right, you've already got 8 electrons in there. Anytime you start bonding, you're going to exceed that octet rule. So our xenon here is going to do 2, 4, 6, and then 8, right? So it's going to, so in our chlorine trifluoride, the chlorine is going to expand its octet because each of these fluorines has to have a bond to it. So we've got 2, 4, 6. The fluorines maintain their octet, the chlorine expands it. In our xenon trioxide, all right, we've got 2, 4, 6, 8 around our xenon. Everybody is going to obey the octet rule. Radon, which is a noble gas, is going to accept extra electrons. So here's our radon in the middle. We have to hook up to each chlorine, so we're going to have 2, 4. Our leftovers would go in the middle, 6, 8. Right, so 2, 4, 6, 8, 10. Right, beryllium is going to be deficient, right? It's right between lithium and boron, so it's only going to form 2. Right? Iodine will exceed the octet rule, and iodine tetrachloride. So we've got 1, 2, 3, 4 times 2, 8, and then our extra electrons make it 10, 12 on iodine. Section 311, resonance. One of the issues and limitations with our Lewis model is that sometimes you can draw more than one totally acceptable Lewis structure for a given molecule. So if you look at the nitrate ion, I've got 3 possible ways I could draw this, right? So my NO3 minus, I've got 24 valence electrons. I'm going to form some happy single bonded oxygens. My nitrogen is going to end up with a double bond and a single bond to two oxygens, but there's no real rule that says, well, why does it go up? Does it go to this oxygen over here to the left? Does it go to the oxygen over here to the right? Like what's happening with these molecules? And so what we can do with that, section 311, resonance. Lewis structures are going to tell us how our molecules are built, how they're hooked together, but a problem arises when more than one valid Lewis structure can be written for a particular molecule. So if we look at this nitrate ion, we've got NO3 minus, 24 valence electrons. We're going to put nitrogen in the middle. We're going to have an oxygen, single bonded oxygen, another single bonded oxygen, and then a double bonded oxygen. But there is nothing to say whether it's going to go to oxygen up at the top oxygen, the left one, or the right one, right? And so resonance is what we invoke to help explain what do we do if we've got three possible Lewis structures and reconcile the reality that all of those oxygen-nitrogen bonds are all actually equivalent. So let's look at the Lewis structure for ozone, right? Ozone's a great example. We've got 3 times 6, 18 valence electrons. Each oxygen is bringing in 6. You know, we start off with step 1. We draw our backbone. We use 4, right? Then we put all of our spares around the side. I pull it on the outside, and then we're like, okay, this oxygen in the middle, he doesn't have enough, so we're going to take some from one of our oxygens, right? And we're going to form a double bond over here, and we'll have a lone pair up on here, but well, why isn't that lone pair necessarily going to the other side, right? So we've got this. Are we going to move the lone pair from our left oxygen, or are we going to move it from the right oxygen? And what we see when we look at an actual ozone molecule is that it's kind of neither of those things, and that we have a molecule that's got what we call resonance with it. Experimentally, ozone has 2 identical bonds, whereas the Lewis structure requires 1 single longer bond and 1 double shorter bond. Right? And experimentally, rather than seeing a short bond and a long bond, we see a bond that is intermediate in length between the short and the long. So what is it exactly? Well, resonance you can think of as being like a hybrid of 2 structures. The second pair of electrons in the double bonded O3 is delocalized. It's going to be spread out across both bonds. The molecule does not go back and forth between the 2 structures. It's not like one on the left and then one on the right, and then one on the left and then one on the right. It is like a mule, which is a hybrid of a horse and a donkey. A mule doesn't look like a horse half the time, and a donkey the other half, right? So if you think about the resonance in an ozone molecule as being like mixing colors, where I'm going to take blue and yellow and I'm going to get green, which is something completely different, or if I take a lion and a tiger and I mix them together and get a liger, which is pretty much my favorite animal. It's bred for its skill and strength and magic. And this dude, who is, of course, on the Tiger King, right? So if there are 2 or more equally valid Lewis structures for one molecule, like our nitrate, right, we can draw 1 for nitrate, right? We can move this bond around. Those 2 bonds are known to be identical. Our solution is that we're going to draw it like this, where we've got a double arrow indicating that it is a resonance structures, and their average forms a resonance hybrid, which best describes that nitrite ion. Right? This double-headed arrow here indicates that it is resonance. And a lot of these oxo anions, so carbonate, nitrate, sulfate, that are going to have these oxygens in it, a lot of them are going to have resonance structures. So here is carbonate. I can put the bond on the top, the left, or the right. Benzene is a molecule that's got resonance as well. I've got these single bond, double bond, single bond, double bond, single bond, double bond that alternate throughout my carbon ring structure. Right? So I do single, double, or do I do double, single? And really, if we strip away those hydrogens, sometimes you'll see these structures without the hydrogens on them, and then we'll just use a corner to indicate a carbon for simplicity. So it's double bond, double bond, or does it go double, single, double, right? And it's going to, we can draw a resonance structure with a double-headed arrow like this, Or in the case of benzene, we can draw it as a hexagon with a circle in it. Sometimes you'll see like a dashed line to indicate that that bond is not a double bond, but it's kind of spread out between multiple bonds. Another example of where you would oftentimes get into resonance or another violation of this octet rule is if you got an odd number of electron molecules. So something that's going to have like nitrous oxide reacts with oxygen to form nitrogen dioxide. It's got an odd number of electrons from that nitrogen. You're going to need a more sophisticated model to help describe some of those. Sometimes they're just going to be drawn with just a single dot on there, and those are sometimes called radicals or free radicals. So you talk about radical scavengers in biology and how radicals can help oxidize some of your systems. You talk about antioxidants. Right, those antioxidants are preventing the action of some of those radicals, which have that formal charge. All right, so we talked about lots of different resonance structures. We can draw more than one for some molecules. Formal charge is our set of rules for deciding which one is best. Right, so it's used to estimate the overall charge on all possible non-equivalent Lewis structures. So if I got 3 different ways I can arrange my atoms to make a molecule, which one is going to be the most likely one to occur? We can use formal charge as a way to help figure that out. And it's going to determine the number of electrons that each atom owns or sees. It's defined as the difference between the number of valence electrons on the free atom and the number of electrons assigned to the molecule, assigned to the atom in the molecule. So our formal charge is the number of valence electrons minus the number of electrons that are owned by that atom. The valence electrons are assigned to various atoms based on the following assumptions: that lone pairs belong entirely to the atom in question, and that shared electrons are shared equally between the 2 atoms. So we're not going to consider polarity, like if it's got a fluorine in there, we're just going to assume that it's evenly shared. The number of valence electrons is therefore calculated, and the number of valence electrons is the number of lone electrons, and 1/2 the number of shared electrons. So caution. Formal charges are not measured quantities, right? These are things that we kind of calculate. We're using it as guidance. It's not an actual plus or a minus charge that shows up on these atoms. It's useful in determining if a Lewis structure is reasonable, right? But it's not going to be perfect 100% of the time. Our fundamental assumptions about formal charges in evaluating Lewis structures are that atoms and molecules try to achieve charges as close to 0 as possible. So you want to minimize the formal charge as much as you can. Any negative formal charges, we're going to put those on our most electronegative ions. Another one is that we're going to try to alternate plus and minus charges if we can. So if you got like 2 pluses and 2 minuses, you're not going to do plus, plus, minus, minus. You want to do plus, minus, plus, right? So alternate those charges. To calculate the formal charge in an atom, you take the sum of the lone pair electrons on 1/2 of the shared electrons and subtract the number of assigned electrons from the number of valence electrons on the free neutral atom. So our equation is F is equal to V, the number of valence electrons, minus the lone paired electrons plus 1/2 the shared electrons. The sum of the formal charges on all atoms in a neutral molecule is 0, and the sum of the formal charges on all atoms in an ion is going to be the charge of the ion. So if you got a -1 nitrate, you could have a plus and 2 minuses on it, or 1 minus and a 0. The sum of the formal charges on all atoms in a given molecule must equal the overall charge. And if non-equivalent Lewis structures exist, those the formal charges closest to 0 and with any negative formal charges on the most electronegative atoms are considered the best, and you want to alternate. A better definition is that the electron surplus or deficit relative to the free atom that an atom is assigned in its Lewis structure. Right, so we've got our equation: total valence electrons minus our non-bonding electrons and minus 1/2 the bonding electrons. So if we're looking at water, right, we're going to look at this. We're going to look at our hydrogens and our oxygens. So we'll start with our hydrogens. For hydrogens, the original number of valence electrons is 1. Right? I've got no non-bonding electrons, no lone pairs around here. I've got 1/2 the number of bonding electrons. I got 2 that are bonding, so it's going to be 1. So our formal charge on hydrogen will be 0. Right? So it's going to be 0, which we expect because this is going to be a neutral atom or a neutral molecule. Right? On our oxygen, We're going to start off with 6 valence electrons, right? Oxygen comes in with 6. We've got 4 non-bonding electrons, 1, 2, 3, 4, and then half the number of bonding electrons. 1, 2, 3, 4 divided by 2 is 2. So it's going to be 6 minus 4 minus 2. And so oxygen will have a formal charge of 0. Each of the hydrogens has a formal charge of 0 as well. So you can look and see kind of how they are sharing each of these electrons. Let's look at the formal charges in ozone. Right? In ozone, we've got 3 different oxygens. Right? We're going to look at oxygen, red oxygen first. All right? So in our first red oxygen, each of these oxygens will come in with 6. But if I look at the red one, I've got 1, 2, 3, 4 electrons in lone pairs, and then 1, 2, 3, 4 that are involved in bonding. So 6 minus 4 minus half of 4, so 6 minus 4 minus 2 is 0. If I look at this blue one, blue oxygen, it's going to start off with 6. I've got 2 in lone pairs, so 6 minus 2, and then 1/2 of 2, 4, 6, so 6 minus 2 minus 3 is going to be plus 1. Right? If I look at this guy over here on the right, my singly bonded oxygen, it's got, starting off with 6, it's got 2, 4, 6 electrons in lone pairs. So it's going to be 6 minus 1/2 of 2 in here. It's going to be -1. A Lewis structure with no formal charge is generally going to be better than one with formal charges. Small formal charges are generally better than large formal charges. Negative formal charges should be on the more electronegative atoms. So for example, we've got carbon, hydrogen, oxygen, and hydrogen, C2H-O. Right? Do I do this as this linear molecule with hydrogens on the outside, because hydrogen's never going to be in the middle? Or do I do it as a carbon in the middle with hydrogen and oxygen around it? Well, let's take a look. If we take our linear molecule here, right, and we draw its Lewis structure, we're going to end up with a carbon double bonded to an oxygen. We'll have 2 electrons in lone pairs on the carbon and 2 electrons in lone pairs on the oxygen. If we compute the formal charge here, right, we're going to do 4 minus 2 minus 2, 4, 6 divided by 2. So 2 minus 3 is going to be -1. We're going to put a negative charge over here, -1 on this carbon. And if we look at our oxygen, right, our triple bonded oxygen, we're going to have 2. So it's going to be 6 minus 2 minus 2, 4, 6 over 2 minus 3, it's going to be +1. Right, so here we've got a -1 and a +1. Is this, we're going to compare that to our other molecule, right, where we're going to end up with a carbon in here with a net ionic or a net formal charge of 0. So it'll do 4 minus 0 minus 2, 4, 6, 8 divided by 2. So 4 minus 0 minus 4 is 0. And then on our oxygen, we'll do 6 minus 4. And then minus 4 divided by 2, 2. So it's going to be 6 minus 4 minus 2, 0. Right? So looking at our rules for formal charge, we want to minimize the amount of formal charge. This one minimizes the amount of formal charge. So we're going to select this as our best possible structure. We also, in addition to not having the presence of charges, we're going to have those at 0. We don't want to put this oxygen with a +1 if we can help it, because oxygen is a pretty electronegative atom. Right? So let's give some possible Lewis structures for xenon trioxide, an explosive compound of xenon. Which Lewis structure or structures are going to be most appropriate according to the formal charges? So with our 26 valence electrons, we're going to draw the following possible Lewis structures. We can have ones where we're single bonding the oxygen to the xenon and put a -1 charge on our xenon, and a -1 charge on our oxygens and a +3 charge on our xenons. We can do one where we've got 0 from a double bond to this oxygen, a +2 and -1 on each of these. We can have one where we've got a -2, a -1, a 0, and a -1. We've got a +2, 0, -1, -1. We've got one where we've got 0s on all the oxygen, 0 on the xenon. Right? So based on the formal charges, right, we can predict that the Lewis structures with the lowest value of the formal charges would be the most appropriate for describing the bonding in xenon trioxide. All right, so we're going to pick this guy over here. Based on the ideas of formal charge, it can be predicted that Lewis structures with lower values of formal charge would be most appropriate for describing that xenon trioxide. If we consider the Lewis structure for phosphorus oxychloride, we can assign formal charges for each thing in this molecule. For the phosphorus, we're going to start off with 5, and we're going to subtract 2, 4, 6, 8 over 2. So 5 minus 4, this guy's going to be a +1. For this oxygen with a single bond on it, we already did an oxygen with a single bond. It's going to be 6 minus 2, 4, 6 minus 2 over 2 minus 1. It's going to be a -1 on the oxygen. And the chlorines are going to start off with 7 valence electrons, minus 2, 4, 6, minus 1, so 6, 7. So these guys are going to be 0 on the chlorines. So it'll be +1 on the phosphorus, -1 on the oxygen, 0 on the chlorines. That's a pretty good stable structure. You can figure that's likely to be a molecule that would exist. And resonance are useful because they help us decide the plausibility of our different Lewis structure. In general, our Lewis structures are written so if the formal charge is as close to possible as 0, and if formal charges arise, we want to minimize them. Section 3.12. Section 3.12